All right, you get your textbooks out, open up to page 174. We're going to talk about your reading that you did last night, and then also look at the homework that you attempted last night and see if you were able to put 2 and 2 together and come up with something that wasn't a fraction. So, or come up with 4, I mean. So anyway, let's review some things though before we do. Couple types of variation that we talked about. And yesterday I botched it, so let's see if I can get it right this time. Let's see if Michael can get it right this time. 2 types of variation that we'll see in our equations.
Direct and inverse.
Direct and inverse are our 2 types. What are the equation forms for direct and inverse variation? Genesis?
Direct is y equals k x. I was going to say b x. And inverse is y equals k over x.
Good. What's the alternate form for inverse variation? It's a little easier to use. This is a good test answer if I ask what is the form for inverse variation. But as far as practically using inverse variation, what's the better form to use, Brandon?
X, y equals k.
There we go. Now, are we always going to use the letters x and y? No. Right? We'll adapt the letters to whatever actually suits the problem we're working. But the key is you've got to solve what value in every case, class. You got to figure out what the k is so you actually have a formula to go off of. What do we call the k in each case, Maddie? Yeah, the constant of variation. You know, k, constant, if you couldn't spell. All right, k for constant of variation. And again, that value is going to be different for every problem that we work. But the key is to figure out what it is for that particular problem. And then once we've found it, you could do other problems following up on that known value. If we were to define direct variation, obviously we've got 3 things here, right? We've got a letter that's by itself, class, we call the dependent variable. We have the k, which is going to represent our constant, because in each scenario it will be constant. And then we've got the x, which we'll call our independent variable. How could I define direct variation then, Abby? How can I define, like in words, direct variation? We see it presented here, but how would I define that in words?
The independent times the constant equals the dependent.
Good. Or we could say the dependent is a multiple of, it's product of something, and the independent is the multiple of the independent variable. Where an inverse variation, Audrey, how would we define that differently?
Both variables are
trying to take what we see in equation, put it into words. Michael, can you help her? How can we define this? We've got 2 equations, so there's 2 ways we could define inverse variation.
What's your question?
Define inverse variation. I gave you 2 definitions.
When one goes up, the other goes down.
Okay, more or less, yeah, that's true. That's a practical way to see, okay, this must be inverse, not direct. If you see, hey, one's going up as the other's going down. But based on the equation form here, we could say that the product of the variables is constant. That's what you were trying to think of there. Or we could say, just as we said here, the dependent is a multiple of the independent. The dependent's a multiple of the reciprocal of the independent. So different ways you'll see that presented with their definitions. Okay, so know the definitions, know the forms there for those. All right, what we started looking at yesterday, or last night in the homework, was this idea of a function. So in your notes, go and write this down. Let's go and get some terms down. And let's go and define what a function is. A function is just a special type of equation. Here's your definition. It's an equation for which each value put in for the IV, we'll abbreviate instead of writing out independent variable, an equation for which each value put in for the IV yields only one value for the dv. An equation for which each value put in for the independent variable yields only one value for the dependent variable. Of course, we'll abbreviate dv or IV and dv there. In other words, you put in 1, you get out 1. You put in a number, it spits out a number. For instance, if we have the equation y is equal to 3x, let's just suppose our constant variation is 3. If x is 5, class, then y is 15. If x is -7, y is nothing else, just those numbers? Yeah, you plug in one, you get out one. This is considered a function because you plug a value in, you get one value out. That make sense? Even this would be the same way, right? If we said that y is equal to 5 over x. Okay, well let's suppose x is equal to -10. What would y equal, class? -1/2. What if we said x is equal to 1/3? What would y equal? 15. Multiply by the reciprocal, so multiply by 3 is 15. But still, you put in a single x, you get out a single y. Make sense? Plug in one, get out one. That would be an example of a function. Here's something that would not be a function, for instance. 2y squared equals x. If x is 8, what's y? And -2. Plug in one, get 2 output values. Not a function. Make sense? So a function, and all that you were reading about in the reading last night was basically to emphasize the point that a function, you plug in one, you get out one. Now there's some different ways that you'll see this, but I first want to explain this idea of function, okay? Where the term comes from. Well, we'll use, obviously, y equals mx plus b for a lot of what we've been doing with graphing, right? The slope-intercept form. And the idea is this, that as we plug in an x value, y values change, right? All along a linear equation, for instance, maybe we have the this point 2, 0, or 0, 2 rather. We have this point, maybe it's 4, 6. We have this point, maybe it's, I don't know, 5, 8, whatever. You're making up numbers here. But for every x value you plug in, you're going to get out a specific y value. Again, this would be an example of a function, a linear function. But the y value depends, hence the name dependent variable, on the x. Therefore, we could think of it as the y is simply a function of the x. It's so dependent to it. So that's where the terminology comes from. There's some different ways, though, that you can determine whether or not you have a function. One, I suppose, would be looking at the equation and coming up with it that way, but the book presents some different options. Look if you go to page 175. I'm going to start with what they call method 3, okay? Another way to represent a function is a graph. And you see a couple of graphs there. Notice the first graph is the function y equals 1/4 x squared. You get this curved shape. Any of you remember from years past what that curved shape is called? If not, it's not the end of the world, but you do. Parabola. Yeah, it's called a parabola. And we have a similar parabola turned sideways because they switched where the x and the y's were. That is that x equals 1/4 y squared, and that parabola turns sideways. In the first graph, if you were to pick a random number to plug in for x, you would get one y value, and only one. That first graph is an example of a function, but we can tell just by looking at the picture. Y'all like that? Easy? I like easy as well. You can tell that an equation is a function, and it shows this to you with your parabola. It says if you do what's called the vertical line test. You remember seeing that term, I hope, in your reading. A vertical line test basically says this. If you pass a vertical line anywhere over the graph, it would cut the graph at only one point. Well, this vertical line only cuts it there. That's 1 point. Vertical line cuts it there. 1 point, cuts it there. Each vertical line would only ever cut the graph at 1 point. Why? Because at no time is there a second x for a specific y value. There's one specific y, for each x value. This would be an example of a function. But you notice on the other parabola, once they turn it sideways, past the vertical line, notice for this particular x, there's two different y's. Fails vertical line test. You know what that means? That ain't a function. So the idea behind the vertical line test as you were doing your reading was, if a vertical line at any time could cross the graph itself more than once, it ain't a function. Make sense? If it only ever crosses once, function. You could also look at the examples on the next page. If you turn the page, you see letter B there at the very top of the page. Another parabola, this one a lot skinnier. But do you notice they pass that little blue dotted vertical line, crosses once. Well, they could have put that blue dotted line anywhere. It wouldn't hit multiple points on the graph. Look at the next graph, down toward the bottom of the page. Pass that little blue vertical line. They could have put it anywhere on the graph grid. Never would it have crossed the graph more than once. But look at the next little one. It's a inverse cubic there. Well, notice that blue dotted line cuts the graph how many times? 3. Right? That particular blue dot. Now, there are places where the blue dotted line would only cut once. Do you see it? If they'd slid that blue dotted line over like the 4 on the x-axis, then it would have only crossed once, but there was a place, there was somewhere on the graph where if you try to pass a vertical line over it, it's going to cut more than once. Make sense? That's the idea behind the vertical line test, and that's a way of figuring out whether or not a graph is a function. So let's look at your homework now on page 179. I'm curious how well you picked up on these different things as you did just the odds, I believe it went, 9 through 15, the odds. Number 9, what was your verdict? Is it a function or is it not a function? What's your verdict, Kendall?
Non-function.
Not a function, because if you passed a vertical line over that graph, obviously just about anywhere you did it, it would cross more than once. There are places where it would cross not at all. That's actually not a problem. But there are places, lots of them, where a vertical line would cross more than once. What about number 11? What do you think? Function or not a function? Abby?
It is a function.
It is a function. You pass a vertical line anywhere on that graph. I mean, because of the limited viewing square that we get, there's a place where it wouldn't cross the line at all. But nowhere would a vertical line cross more than once. It must be a function. You would plug in an x, you're only going to get the one y value. We can see that from the graph. Number 13, what do you think here, Genesis? Function or not a function? Function. You pass a vertical line over there, at no point is that vertical line going to cross more than once. Must be a function. What about number 15? What you got on that one? Brandon? Not a function. Most of the graph would miss with a vertical line, but there's that small window where no matter where you put the vertical line, it's going to cross more than once. And again, if there's any point where a graph will cross more than once, it cannot be considered a functional equation. Does that make sense? Plug in one, get out one. And from a graph, we would use the vertical line test. From a graph, we would use the vertical line test to determine whether or not we have a function. Does that make sense? Another way we could check is by looking at a list of points. Turn back to page 175. They give you a list of points here on page 175, and they say these points are some of the points, not all of them obviously, that are in a particular graph. -1, 1, -1, 0, 0, -3, 1, -1, 2, 5. Do these points describe a function? Well, remember, if you plug in one x class, you should get out one y value. Are there any repeated x values in this list? The first two, -1, -1, and -1, 0, both of them have an x value of -1, and yet that same x, -1, spat out, so to speak, not literally, two different y's, a -1 and a 0. That's not possible if it's a function. Now, graphs can do that, just not functions. Functions can't do that. Functions are special. Functions are one for one, not one for multiple. So no, that would not be a function. You were checking that kind of thing as well on the odds 1 through 7. Let's see if those describe a function. These were a little harder. I like the picture, but this, a little bit of analysis here. Number 1, what's our verdict? Is it a function, yay or nay, Audrey? Do you see any repeated x's? No, I do see repeated y's, and maybe that's what caught your eye, but repeated y's are okay. For instance, these 2 points have the same y value, but no x value has 2. Here, this one x has 2 different y values that go with it. That's not acceptable. But you can have, different x's have the same y value. So no, that actually is a function because no x's are repeated. Make sense? What about number 3, Michael? What's the verdict? Function or no?
Function.
Function. There's no repeated x's, so we're fine. How about number 5? What's the verdict? Genesis?
Not a function.
Not a function. Which x value is repeated with differing y values?
The 2 middle.
The 8, right? Is an x value that has 2 different y's. Okay, that means it can't be a function. What about number 7? What does that seem to indicate? Kendall?
No function.
No function, because which x has been repeated?
The -7.
The -7's been repeated, and you can't have that to have a function. Does that make sense? Okay, I'm not even going to ask how many got all of them right, because I really don't care. What I care about is, does it make sense now? You read the reading. Well, I will ask. Did anyone understand the reading well enough to get all of them right? Okay, some of you did. Wow, okay, that's actually really good. Most of the time, I give the reading. It really is not so much for you to learn it from the reading, though some people can, apparently. It's really more so you've seen it once, so when I teach it, you're like, okay, that's what that meant. So you're not seeing it for the first time. But some of you did get it. All right, what I want you to do now, let's go through and hit all of the even numbered problems, the 2 through 16 on this page. Let's see if we understand it better now that we've tried it, though some of you apparently had a pretty good understanding to begin with. Show-offs. Putting yes or no, or check mark X, or function, not a function. Yeah, I'm gonna be the last one because I'm lazy. You did that. You wrote function and not a function. You're no mathematician.
That was fast.
Hey, I was proud of Glenn earlier today, Maddie. He came up with a lazy hack to do a problem that even I hadn't thought of. I was like, I thought of one shortcut on this process. He's like, well, couldn't we just do this? I'm like, yeah, bravo, yeah. I was proud of him. Got the makings of a mathematician. I think Genesis is having way too much fun over there, so I'm pretty sure she's done. She's drawing a whole bunch of lines. I'm like, she's still working. No, she's not. Faker. All right, number 2. What's the verdict, class? Yay or nay?
No.
Nope. We got that -3 has 2 different y values with it. That's no good. Think of like the x as being like, the guy, and then he's got 2 different girls with him. That's bad, right? Yeah, that's even Guy knows that's bad. All right, number 4. What's the verdict, class? Yay or nay?
Yay.
Yay, it is indeed a function. Number 6.
Nay.
No, who's in big trouble?
The guy.
The 3. The 3 is in big. 11's fine and 2's fine, but the 3 is in big trouble. Number 8. Yay, it is indeed. At least based on what we see there, there's no reason to believe it's not a function. What about number 10? Yay or nay? Let's go to Maddie. Yeah, seems to be a function. Vertical line doesn't ever cross more than once. We should be good. How about number 12? What's the verdict? Aubrey. I did it again. Audrey. I know who you are. Let's call you misdemeanor instead.
No.
No, not a function. Failure. Number 14. What's the verdict there? Brandon?
No.
Also a failure. What about number 16? What's the verdict? Abby? Yep, it's function. All right, how many went 8 for 8 on the evens? You got all the evens right. Oh, Maddie. All right, which one did you miss? Or ones?
6, because I didn't see the second 3.
I didn't see the 3s repeated. Yeah, and that's really what you're locked in on is, do I see a repeated 3? Now, I will say that what would be really evil of them, okay, would be to give you a set of points, like 2, 5, -3, 7, 4, -1, 2, 5, and like 3, 4. Function or not a function?
Nope.
Yeah, there's no reason to think it's not, because the repeated x actually has the same y both times. Like, that would just be evil. I don't think they ever do that to you, okay? But that's just the mean, twisted person in me is coming out like, anyway. But hey, you work hard and you do your homework and stuff like that, and don't make me angry. And we shouldn't have to worry about that kind of thing showing up on a quiz or test, I am sure. But anyway, yeah, that would be the only time where a repeated x actually isn't a problem. It's like, saw Mr. Nadesky with the school librarian the other day. At the time of this recording, I married the school librarian for the sake of record. All right? And then, well, that's strange because like 7 or 8 years ago, I saw him with the 2nd grade teacher. 7 or 8 years ago, my wife was the 2nd grade teacher. So, it's like, same woman both times, we're still good. We're all fine here. Anyway, probably a horrible illustration, but whatever.
Just a little bit.
Questions on this?
Anyways.
All right, well, let's move on. Another way to determine whether something's a function or not. And I want to go back to the illustration I gave you earlier. we had the equation y is equal to 3x. And we said no matter what you plug in for x, you'll never get more than one y value out, because nothing times 3 gives you more than one value. But we had remember the 2y squared equals x, and we said, well, what if x is 8? Well, the problem is the y squared, right? Because a y squared means I'm going to at some point have to take a square root. And when I take a square root, I'm going to have to get y equals positive, negative, something. It happens to be positive, negative 2. But the problem is if you have a y squared, what should be your dependent variable, the y is always assumed to be dependent, is going to produce a positive, negative. That means it's not a function. So when you're looking at an equation, if the y value would at some point produce a positive, negative, that's an example where you'd end up with multiple values. This can't be a function, I can tell from the equation. Does that make sense? Let's look at some equations now on page 180. So turn the page over. Let's look at some different equations here. Number 17. Would that be a function or not? Well, really the best thing to do would be to actually fully solve for the y. So on number 17, if I fully solve for the y, my thought is let's double switch my negative 4x and my negative y squared to get y squared equals 4x plus the square root of 2. But to finish getting the y by itself, class, I have to do what? Take the square root. Now when I take a square root, I've got to put... So is that equation a function? Nope. Because that means you're going to get two different y values if you only plug in a single x here. That can't be a function. Look at number 19. What would I have to do, first of all, to solve that big ugly thing? Yeah, cross multiply, right? So we've got the 10y plus 9x minus 1. Obviously, multiply that all by 1, you get that. And then multiply the 4x by the 10 class to get 40x. All right, if I want to get the y by itself, let's first kick out the 9x as a negative 9x and kick out the negative 1 as a positive 1. You get 31x plus 1. And then finally divide away the 10. Well, I plug in an x. Am I going to get out multiple y's? No. So this equation must be a function. Looking at number 21. We've got the y minus x plus 12 equals negative 5x plus 10. All right, if we want to get the y by itself, what do I need to do here? Maddie?
Move the negative 5x over is positive.
Well, that's getting something with the y, unless you plan to move the y over later, but do you want to get the y by itself? So I would have actually sent the negative x over. You want to do that instead? Yeah, let's do that instead. Move it over as a positive x, of course, yeah. And that would give us...
y is equal to negative 4x.
There we go. And by the way, here we see a linear equation. All linear equations are functions, by the way, right? Can you ever see a vertical line? Well, check that. There's one linear equation, or one type of linear equation that isn't a function. Can you think of it? A straight line, an undefined line, right? If you have, for instance, you have x equals negative 3. That's here. Well, if I were to do the vertical line test, at any point could a vertical line cross more than once? Yeah, right here it crosses how many times? Infinite number, right? So this, anything x equals whatever, anything with an undefined slope would not be a function. But any other linear equation is going to be a function. I started to say all linear equations are functions, but no, there is that one type there. What about number 23? I see a y squared. So my initial thought would be what, class? Not a function. However, remember I said what you're going to need to do is get the y by itself. This one's a dilly. Volunteer to get the y by itself on this one. Somebody with a big brain. High GPA. They're looking at each other. All right, Kendall, I'll pick you. Why don't you go ahead and help us out here. What do we need to do on 23 to get y by itself?
Move the 10x over.
Well, I'll tell you what. Let's put the 10x plus 2y over 1 before we do anything else. And does that kind of give you a... I miscopied that. Thoughts? There we go. Cross multiply. And we cross multiply here.
10 and x1 2y cubed.
I copy that right? Yep, okay, just making sure. Equals?
2y cubed times 2.
All right, thoughts?
You can cancel the 2y cubed.
Yeah. Now what do I do to get the y by itself?
You can divide the 10x.
And I could actually reduce that down to get
1 negative 5x.
negative 1 over 5x. Is that a function, class? Yeah, no positive, negative. So the reason I showed you expand it all the way up, solve for the y, is because just because you see a y squared, it doesn't mean there will actually be a positive, negative. It's if the y squared ends up by itself, you're going to end up with a positive, negative. Right here, divide away the 2, take the square root, yup, there it is. There's my positive, negative. Here, y equals, and there's the positive, negative, not a function. Here I see y squared, initial thought, oh, this is probably not going to be a function, but end up solving it. Nope, there's not a positive, negative there. That one would be a function. I want you to do the evens now, 18 to 24. Do the evens now, 18 to 24. Determine in each case, is it a function or not? And you're going to have to get the y by itself. By the way, just because an equation is not a function doesn't mean it's like bad or anything. It's just, you know. And that's where my previous illustration kind of loses something. It's technically not a problem to have an equation that is not a function. You just want to spot those that are.
So you know which ones to avoid to help out your illustration.
Well, I suppose maybe. My illustration wasn't pre-planned. That's really the problem, and that's why it needs so much help. Gotta stick to the script. Joe Biden.
Oh, anyways.
Can y'all see that press conference? Yeah, he didn't have a script. As soon as you start taking questions from reporters, unless you pre-script the questions, which they did do for some of his town halls in the election, but unless you pre-script questions, you're going to find yourself in trouble. And you don't actually know what's going on. Or can't remember what lie you told last month. Anyway, getting off politics. Grace Christian School does not officially endorse or support any particular party or candidate. Chapel message though, he's like, you know what, your silver and gold, it's mine. Your wife, yeah, wives, yeah, they're mine. Children, yep, they're mine. All of them mine. Okay. I'm like, well, hey, we want nuclear weapons. Here's $1 billion in cash. Please don't do nuclear weapons. Well, use this $1 billion to help fund our nuclear weapons. Oh, you don't want us there anymore in Afghanistan. Okay, we'll leave. Oh, dang, look what just happened. We left bunches of people stranded and millions of dollars worth of equipment. Huh, how unfortunate. Weak leadership. You know what? And you know all Ben Haddad wanted all along was a fight. Like, he really did not. You have to know, right? Reading behind the lines, there's no way Ben Haddad expected Ahab to say okay the first time, right? Like, you know he's just wanting to start a war. It's just like, what's the one thing that'll make him, like, start a war? Tell him to give me all his money? No, boss. No, you got to ask for his wife and kids, too. That way he won't actually do it. I mean, I guess if I was married to Jezebel, I'd be like, here, take her. You know, but... He's like, oh, man, he said yes. What do we do now? I want to fight. So you're going to take anything you want. And I was like, okay, you went too far. Okay, we're going to fight. You just wanted that all. You missed a great chapel service, Brecken and Gavin and whoever else is watching later on. Great chapel. Great chapel. Anyway, he wasn't trying to go political, by the way. I just happened to pull that little inference out when he went there. I was just struck by what a weak leader Ahab was, and it made me... Anyway, Off politics, back to math. It's much safer. Except for those who are in possession of weapons of math instruction. Number 18. Juniors and senior got there. Got that. All right, number 18. What did you get when you got the y by itself, Michael?
I just put x.
Oh, it's not x.
Yeah.
And when you get the y by itself,
You get y equals 3x over 3x minus 7 plus 1.
Okay, so Michael, we got a y squared times 3x minus 7 all over x is equal to 1. And I'm going to do the same thing with you I did with Kendall. Over 1. What do I do to solve?
You put them under the same denominator.
Cross multiply.
Oh yeah.
Yeah, cross multiply. What do we get when we cross multiply?
Y squared times 3x minus 7 is equal to x.
Now how do I get the y by itself?
You divide away the 3x minus 7.
And then,
Y squared. You square it.
that's already
Square
squared.
root.
Take the square root. So is it a function or not?
No.
Not a function because of what we get when we solve for the y.
That's
Making
correct.
sense?
I put x as in not a function instead of like the letter x. Sorry. I did check marks and x's.
Oh. I wanted the equation.
Oh.
That's the equation. And therefore, it's not a function. Number 20. What's the verdict on this one? Or what do we get actually initially on this one? Audrey? It's absolute value, right? So technically you have to make two equations, right? Y equals the 8x plus 1 and y equals the negative 8x plus 1. Or we could say y equals positive negative 8x plus 1. So function or not a function? No, because of the absolute value kind of does a similar thing to a y squared in that it creates a positive negative. That means 1x is going to give you 2 y's. You can't have that. What about number 22? What's your equation when you isolate the y? Maddie? 6x plus a half, so yeah, that's a function. What about number 24? What did you get when you solved for the y on this one, Abby?
I got y equals, I had y squared still.
Okay, so we had you had y squared equals what?
Well, 10x squared plus 3x equals y squared plus 3x squared.
Okay, so we subtract away the 3x squared to get the y squared by itself, right?
Yeah.
And that gives us,
2 answers.
well, yeah, but initially, simplifying it down, good algebra practice.
Equals this x times what?
How about 7x squared plus 3x?
Oh, I was
Combine like
trying to
10?
get the square root of
And then take the square root.
Oops.
And we get that. And because it produces a positive negative, what's our answer? Not a function, because it produces positive negative. Questions on this? Get the y by itself. All right. Now, let's talk about the next thing in your notes. Let's talk about something called function notation. Function notation. Notation refers to the way something looks, the way something is written, right? We talked before about inequality notation versus interval notation. These mean the same thing, they're just written different ways. That's what notation means. Function notation basically means we're going to take a function, but we're going to notate it or write it in a different way. For instance, y equals 3x plus 2. Function or not a function, class? Function. There's no positive negative there, so it's function. And so what we could do is we could say, well, okay, if x equals 2, then what does y equal? 8. Right? Easy enough. You just plug the 2 in for the x and you get the 8. Function notation replaces the y with what the y really is. The y is a function of the x. It's dependent on the x, right? And so we'll replace the y with this notation, f of x. And it's read f of x. Now, of doesn't mean multiply here. We're not multiplying f times the x, but it's read f of x equals 3x plus 2. All we did is take the y and replace it with an f of x. And now instead of saying if x equals 2, then y equals what, we'll simply say f of 2 equals what? But we do the same thing. This means that 2 goes into this function wherever you see an x. I see an x, I'm going to put a 2 there. There's an x, put a 2 there. What do I get? 8. Same thing we got last time. Same equation, right? It's written different. It's notated differently, this function notation. And the upside of this is it allows the mathematician then to very quickly find functions of other values. What about f of 4? Well, again, that means now, instead of my x, I'll plug in a 4 class. And f of 4 is?
16.
14.
Oh, yeah.
If I have f of negative 1, well, that means right here where I see an x, I put a negative 1. And what do I get, class? Negative 1. Do we see how function notation works? Genesis, I'm not sure what you're writing. Questions on this? You're just copying it all down? Are you thinking about what you're copying? Okay, just making sure. I don't want to lose you and be like, what did he just do? Because you're busy writing, and I want the brain engaged more than I want you writing right now. It's just another way of writing it. So in fact, for graphing, not always, but thinking more down the line in the future, at some point our Cartesian planes will be written as x and f of x axes, not x and y. Well, f of x just means y. Y is a function of x. It's the dependent variable depending on x. It's a function of x, so we can replace y with the f of x. But by using what's called this function notation, it allows us to quickly solve multiple values without having to write out if x equals this, if x equals that. It's just f of this. So write this down in your notes. F of x equals 3x minus 8. We're given a function of x is 3x minus 8. It's a linear function, right? Y equals y, essentially, equals mx plus b. We know the y-intercept is negative 8. We know the slope is 3. That's slope-intercept form still. We're not interested in graphing it. The question is, what's f of 1? Well, when I say that, that means in for the x, plug in a 1. And if I plug in a 1 for the x, what value do I get out, Kendall? Negative 5, because 3 times 1 is 3, minus 8 is negative 5. What about f of negative 2? F of negative 2. Michael?
Hold on, I'm trying to write it out so I remember.
Still?
Yes. I'm going blank.
Okay.
I forgot how to do math.
Okay, where it says x, I plug in whatever I said f of. So I'm going to plug in
Negative 2.
for the x. And then the math tells me to multiply 3 times negative 2,
Negative 6.
and then subtract 8 from that.
Negative 14.
There we go. All right, what about f of 0? Audrey? Negative 8. Because 3 times 0 is 0, minus 8 is negative 8. Now, we can use other letters. We say f of x, but there are times where mathematicians will work with multiple functions at once. And so, rather than all of them being f of x and them getting very confused and not being able to refer to, well, which f of x? Well, the third one on the left, whatever. So we'll use different letters. For instance, they might say g of x. G isn't a letter that's used often in math anyway, right? A's, B's, and C's are, X, Y's, and Z's are. The rest of the alphabet really goes largely unused. So we'll say g of x, for instance. And we can say maybe g of x equals 4x squared plus 1. Well, just because it's g of x doesn't change anything. The process is still the same. If I said I want you to find g of 3, well, this means instead of an x, we're going to replace it with what value, class? 3. So Genesis, if we replace the x here with a 3, what do we get for g of 3? 37. Okay, 3 squared is 9, times 4 is 36, plus 1 is 37. What about g of negative 2? What will we get then, Brandon?
17.
Good. Negative 2 squared is positive 4 times 4 is 16, plus 1 is 17. What if I wanted to change it up? Maybe go with h of, and maybe I don't even want to go with x anymore. Maybe I want to say h of m, a function of m. But we'll go h of m. Is equal to m squared minus 3m. Again, I don't have to stick with conventional letters necessarily. So you see the flexibility. Now, if I were graphing this, I'd have an m axis and an h of m axis. Whatever, okay. But it's still same thing, dependent or independent and dependent. But if I wanted to find h of negative 4, now notice, there's 2 different m's in here, aren't there? 2 different places I've got to plug in a negative 4. So I'm going to plug in a negative 4 here and square that, and then I'm going to multiply the negative 4 here by that negative 3. Both times you have to plug in that negative 4. Make sense? In other words, this h of m means anywhere you see an m, or anywhere you see this number, plug it in for the m. Plug it in both places. What do we end up with for h of negative 4? Abby?
Wait, I was going to say 4, but negative 4 times negative 3 is positive 12.
Right.
So, 28.
Good. This is a positive 16. This gives you a positive 12, as she noted, which gives you a positive 28 for your answer. What about h of 5? H of 5, what do we get for that? Maddie? Oh, I had to go. I didn't do it on purpose, I promise. That is correct. People watching, I couldn't hear it. You don't need to hear it. You know what the answer was. All right, 10. All right, I didn't think about that one too well. All right, it could even look weird with fractions. I could do like f of a or something like that. And I could say is 4 over a minus 2. You know what's called a rational function here, right? Where I have the variable in the denominator. That's fine. We can still work with it. Let's suppose I wanted to find f of, let's go with 3. What is f of 3 going to be here, Michael?
4/3 minus 2.
Careful.
Oh.
Remember, the grouping is grouped down here, so it's going to be the 3 minus 2 first.
4.
4. There we go. 4 over 1, or just 4. What about f of 1? Genesis? And we're going to start by plugging the 1 in here where the a is, so 1 minus 2. And then 4 divided by negative 1.
4 divided by negative.
Is
Negative.
negative 4. What if I had f of 6? What would I get for that value? Audrey?
4/3.
Careful.
1.
Plug me the 6 down here.
1.
There we go, 1. 4 over 4 just gives us a 1. Do we understand how function notation works? Questions on this? Because we're going to do a lot with function notation in the days ahead, but questions on the basics of function notation for now. Make sure we got a basic understanding. Let's have you practice some of these. Do 25 to 30 there on page 180. 25 to 30. Now, they didn't use the function notation of the tail end. They said where x equals 5, where x equals negative 2, instead of just saying f of 5 or g of negative 2. Michael's got him. Brent's got him. There you go, guys. Abby's finished. That was a close one. Nothing against Abby. Audrey's finished. I promise I don't really like the guys better than the girls. I don't. Not playing favorites or anything. let's go and take a look at these together. We're finding f of 5. It says when x is 5. So we plug in the 5 squared class, 25. We do negative 12 times 5, negative 60. And then we add 2. And if you need to, use your calculator. No shame in that at all. We get negative 33. How many had that answer for number 25? All right, the next one, g of negative 2. So we're going to square the negative 2 class. We're going to multiply negative 2 times 4. And then subtract the 11. We end up getting negative 15 for g of negative 2. How many have that? Question? Did you have? 1. Oh, you had the positive. All right. Looking here, h of 3. So we do 3 minus 4 class. And 3 plus 8.
11.
Yeah, that's unsatisfactory. What's our answer?
Negative 1/11.
Negative 1/11. And there's our answer. How many had negative 1/11? Don't forget to slide the negative out front. Question.
I had negative 1/5.
Making sure I copied it. No, that's a 3, and that's an x plus 8. So yeah, 3 plus 8 would be 11. So maybe just copied something wrong. I don't know. All right, look at the next one. Q of negative 1. 2 times negative 1. Negative 2 plus 1. All right, 3 times negative 1. Negative 3 minus 7. Answer this time, 1/10. Positive answer this time. How many have the 1/10? Questions on that one? Look at the next one. F of 8. Well, we're going to take the 8 times the 12, 96 minus 15, and the square root of 81. Now, if they didn't already have the square root there, it would be, but we can't have a positive negative, can we? Because that would be 1 input, 2 output. The fact that the square root is here with the understood positive means they want the positive principal root. Had they had a negative here, that would imply they wanted the negative root. If they'd had positive negative here, they couldn't use function notation. They have to say y equals, because function notation is reserved for actual functions. And if there's a positive negative, it is not a function. So we'll just go with the positive 9. How many had the 9 for that one? How many had positive negative 9? And again, understandable thought. Does it make sense now why it's just the positive? And again, the way I taught it to you before was if you take the square root, like the square root symbol wasn't there, you put it there, then positive negative. Well, it was already sitting there with an understood positive in front. So same thing's going to happen here. We plug in our negative 7 to find f of negative 7. Negative 2 times negative 7? Positive 14 plus 9. Can I take the square root of 23? Can I reduce the square root of 23? What do I get? 4 times the square root of 23. We'll just leave it big, ugly, irrational value. How many have that answer for the last one? Questions on function notation. And then we can go 6 for 6. You got them all. Okay, good Genesis. 5 out of 6, just missed 1. Most of us, all right. 4 out of 6. Okay. We understand the 1 or ones we missed. All right, homework for the weekend. Read pages 181 to 186. Read pages 181 to 186. So that way when I teach it to you on Monday, it's not the first time you've seen it. Read 181 to 186. On page 187, do numbers 1, 3, and 5. Page 187, do 1, 3, and 5. And on pages 188 to 189, do 15 to 27, the odd. Pages 188 to 189, do 15 through 27, the odd. Again, that's page 187, 1, 3, and 5. Page 188 to 189, 15 to 27, the odd, after you read pages 181 to 186. All right, with the bell rings, you'll be dismissed. Have a wonderful rest of your day.